We often think of time as a constant, a universal drummer that beats at the same rhythm for everyone, everywhere. We imagine a grand cosmic clock ticking away the seconds, minutes, and hours with an unwavering, absolute pace. But what if I told you that this universal clock doesn't exist? Time is not a rigid, unchangeable river flowing at the same speed for all. Time is flexible. It can be stretched and squeezed, flowing at different rates for different observers. This isn't science fiction, it's a fundamental property of the cosmos. The universe has many clocks, and they don't all tick in unison. The most extreme examples of this temporal weirdness are found near black holes, regions where gravity warps the very fabric of reality. Near a black hole, the steady tick-tock of time slows to a crawl. An hour there could feel like a lifetime elsewhere. So let's embark on a journey to the edge of one of these cosmic monsters, where our understanding of time is challenged and transformed. Prepare to have your perception of the universe fundamentally altered. For centuries, Newton's universe had time as absolute, marching forward relentlessly, the same for everyone. But then Einstein came along and asked, what if time and space are interwoven into a single dynamic fabric? Einstein's general relativity proposed that gravity is not a force, but the warping of space-time by mass and energy. Imagine a heavy ball on a rubber sheet. Objects follow the curves, not a direct pull. If space can be bent, and time is woven with space, then time must be bendable too. The stronger the gravity, the more space-time is curved, and the slower time flows. Time passes more slowly in regions of stronger gravitational pull. Your feet age slower than your head. This concept, gravitational time dilation, shattered the idea of a universal clock. Now, the universe is filled with countless personal clocks, each ticking at its own rate, dictated by local gravity. Einstein gave us a cosmos, where time is relative, malleable, and inextricably linked to gravity. To grasp time dilation, let's come back to Earth with two synchronized atomic clocks. Leave one at sea level, take the other to a mountaintop, and let them run for a year. Intuition says they'll stay synchronized, but Einstein's theory predicts otherwise. The mountain clock, farther from Earth's center and in weaker gravity, ticks slightly faster than the valley clock. The difference is tiny, just microseconds, but it's real and measurable. Time on the mountain literally flows faster than in the valley. This experiment has been done, confirming Einstein's prediction. Time is not absolute, its flow is influenced by gravity. If a small altitude difference can create a measurable time shift, imagine what happens near a black hole. There, the tale of two clocks becomes truly epic. So, what are black holes? They're what's left when a massive star collapses under its own gravity. The star's matter is crushed into a point of infinite density, a singularity, where physics breaks down. The gravity is so intense it warps space-time to an extreme. Imagine dropping an infinitely heavy pinhead on our rubber sheet. It punctures the fabric, creating a bottomless pit. This is a black hole. Its pull is so immense that not even light can escape once it crosses the event horizon. The event horizon isn't a surface, but a boundary where escape velocity exceeds the speed of light. Anything crossing it, spaceship, planet, or light, is trapped forever. From the outside, you'd see objects slow down and fade as they approach the horizon. Black holes are the universe's ultimate gravity wells, where time is distorted in the most dramatic ways. They are perfect laboratories for exploring the true nature of space-time. What happens to time near a black hole? As you approach the event horizon, gravity grows extreme and time slows dramatically. Imagine orbiting a supermassive black hole while your friend watches from far away. For every hour you experience, years or decades might pass for your friend. The closer you get to the event horizon, the more extreme the time difference. At the event horizon, your friend would see you slow down, your image freezing on the edge of the abyss. From their perspective, you never actually cross the event horizon. Time for you appears to stop. This is the ultimate expression of gravitational time dilation. At the edge of a black hole, time, relative to the outside universe, comes to a standstill. The ticking of the clock ceases, stretched into an infinite moment. For distant observers, the event horizon is where forever is frozen. This isn't just theory, it's a direct prediction of Einstein's equations. The idea of extreme time dilation near a black hole was brought to life in the film. In the movie, astronauts land on a planet orbiting close to a supermassive black hole, Gargantua. Time there passes so slowly that 1 hour equals 7 years for those far away. When the astronauts return, their crewmate has aged 23 years while they've barely aged at all. This scene powerfully illustrates the real human consequences of gravitational time dilation, turned Einstein's mind-bending concept into a compelling story for millions. To visualize gravity's effect on space and time, picture a stretched trampoline, the fabric of space-time. A marble rolls straight across a flat sheet, no gravity, time ticks evenly. Add a tennis ball, it creates a small dip like our sun, curving the marble's path and slowing time slightly nearby. Now a heavy bowling ball makes a deeper well, like a star or planet with more significant curvature and slower time. Drop an ultra-dense object, a singularity, and you get a bottomless pit, a black hole. Any marble too close spirals in and disappears. This is the event horizon. In this deep funnel, the fabric is stretched to its limit. Time slows to a crawl. The deeper you go, the slower time passes relative to the flat parts far away. This simple visual shows Einstein's insight. Gravity is the shape of space-time, dictating how objects and time move. The universe's weirdness is written into the very fabric of reality. Imagine you're an astronaut near a black hole. To you, time feels normal, your watch ticks, your heart beats, coffee cools as usual. But look out the window, the universe outside ages at a frantic pace. News from Earth flashes by, decades pass in minutes, loved ones grow old in a blur. Meanwhile, a friend watching you from afar sees you move in slow motion, every action stretched out. If you approach the event horizon, you appear to freeze, a static image on the edge of space-time. Your time is normal to you, but to others it's nearly stopped. This duality is the heart of relativity, no single truth about the flow of time. For you, the traveler, time is normal, for the observer, it's slow. This journey makes you a time traveler, leaping into the universe's distant future. It's a one-way ticket to forever. Are black holes time machines? In a way, yes, they let you travel into the future. Spend a year orbiting a black hole, return to find centuries have passed on Earth. This isn't just theory. We see a tiny version on the International Space Station. Astronauts age a fraction of a second slower due to speed and gravity. A black hole magnifies this effect. Thousands or millions of years could pass outside. But there's a catch. It only goes one way. General relativity doesn't allow travel to the past. Backward time travel remains science fiction. Black holes offer a one-way ticket to the future, not a round trip. They remind us that the universe is a place of profound wonder, where time and space are flexible. Time is not a rigid ruler but a flowing river shaped by gravity's pull.